Welcome. Today, we're diving into the fascinating world of agents and artificial intelligence. Agents are entities that perceive their environment and take actions to achieve specific goals. In AI, agents are grouped into five main classes, each with its own level of intelligence and capability. These classes are simple reflex agents, model-based reflex agents, goal-based agents, utility-based agents, and learning agents. Over time, all these agents can improve their performance and generate better actions. In this video, we'll explore each type in detail, understand how they work, and see how they fit into the broader landscape of AI. Let's get started by looking at the simplest kind of agent. First up are simple reflex agents. These are the most basic type of agents. They select actions based solely on the current percept, which means they ignore everything that happened before. Their decisions are made using condition action rules, often called if-then rules. For example, imagine a vacuum cleaner that decides where to clean based only on its current location and whether there's dirt present. It doesn't remember where it's already cleaned or what it did before. This approach works well in fully observable environments where the agent can see everything it needs to make a decision. Let's look at a practical example. The vacuum agent is a classic simple reflex agent. It checks its current location. If there's dirt, it cleans. If not, it moves. This decision is made without considering any previous actions or locations. The agent's behavior is entirely reactive, responding only to what it senses right now. This makes simple reflex agents easy to design and implement, but also limits their intelligence. They can't adapt to changes or remember past experiences, which can be a significant drawback in more complex environments. Simple reflex agents are straightforward. They come with several limitations. Their intelligence is very limited because they don't have knowledge of anything beyond what they currently perceive. In environments that aren't fully observable, these agents can easily get stuck in infinite loops, repeating the same actions without making progress. They also can't handle situations that require memory or understanding of the broader context. As a result, simple reflex agents are only suitable for very basic tasks in predictable environments. Overcome the limitations of simple reflex agents, we have model-based reflex agents. These agents can operate in partially observable environments by keeping track of the world state. They use a model, which is knowledge about how things happen in the world, and an internal state, which represents what the agent has perceived over time. By combining current perceptions with their internal model, these agents can make more informed decisions, even when they can't see everything at once. Model-based agents update their internal state by considering two key pieces of information: how the world evolves and how their own actions affect the world. This means they don't just react to what they see right now, they also use their understanding of how things change over time. For example, if an agent knows that cleaning one room will make the next room dirty, it can plan its actions accordingly. This ability to track and predict changes makes model-based agents much more flexible and capable than simple reflex agents. Let's visualize a model-based agent in action. Imagine a robot navigating a house. It remembers which rooms it has already cleaned and predicts where dirt is likely to appear next. By using its internal model and percept history, it can make smarter decisions about where to go and what to do next. This approach allows the agent to handle more complex and dynamic environments, adapting its behavior based on both current and past information. Moving up in complexity, we have goal-based agents. Sometimes knowing the current state of the environment isn't enough for an agent to decide what to do. Goal-based agents have an additional component, a goal. This goal describes a desirable situation that the agent wants to achieve. By considering its goal, the agent can choose actions that move it closer to success, rather than just reacting to immediate circumstances. Goal-based agents expand on model-based agents by incorporating goal information into their decision-making. They don't just react or predict, they actively plan. These agents may need to consider a long sequence of possible actions before deciding which one will help them achieve their goal. This process, known as searching and planning, makes goal-based agents proactive. They can evaluate different scenarios and choose the best path forward, even in complex environments. Imagine a delivery robot that needs to deliver a package to a specific location. It doesn't just wander around, instead it plans a route that will get it to its destination efficiently. The robot considers different paths, obstacles, and possible actions, always keeping its goal in mind. This ability to plan and search for solutions sets goal-based agents apart from simpler types. Next, let's talk about utility-based agents. These agents are similar to goal-based agents but add another layer: utility measurement. Utility is a way of quantifying how desirable a particular state is. Instead of just achieving a goal, utility-based agents aim to achieve the best possible outcome. They evaluate different actions based on how much utility or satisfaction each one provides. Utility-based agents use a utility function to map each possible state to a real number. This number represents how well the agent's goals are being met. When faced with multiple alternatives, the agent chooses the action that leads to the highest utility. This approach is especially useful in situations where there are many possible outcomes, and the agent needs to pick the best one, not just any that achieves the goal. Consider a self-driving car that needs to choose the safest and fastest route to a destination. It doesn't just look for any route that gets it there. It evaluates each option based on factors like traffic, safety, and time. The car uses a utility function to score each route and selects the one with the highest utility. This ensures the agent not only achieves its goal but does so in the best possible way. Finally, we come to learning agents. These agents have the remarkable ability to improve their performance over time by learning from their experiences. In artificial intelligence, a learning agent is designed to adapt and evolve, making it more effective as it encounters new situations. Learning agents are essential for tasks where the environment changes or is too complex to be fully understood in advance. Learning agent is made up of four main components. The learning element is responsible for making improvements by learning from the environment. The critic provides feedback to the learning element, helping the agent understand how well it's performing. The performance element selects and executes actions based on current knowledge. Finally, the problem generator suggests new actions that lead to informative experiences, enabling the agent to explore and improve. Imagine a robot that learns to navigate a maze. At first, it might make mistakes, but over time it learns which paths lead to success and which ones don't. The learning element updates its knowledge, the critic evaluates its performance, and the problem generator encourages it to try new routes. This continuous cycle of learning and improvement allows the agent to become more effective with each attempt. Now that we explored each type of agent, let's compare them. Simple reflex agents are fast and straightforward but limited in intelligence. Model-based agents add memory and prediction, making them more adaptable. Goal-based agents introduce planning, while utility-based agents focus on achieving the best possible outcome. Learning agents stand out by continuously improving through experience. Each type has its strengths and is suited to different kinds of tasks. Designing an AI system, it's important to choose the right type of agent for the task. Simple reflex agents are great for predictable, fully observable environments. Model-based and goal-based agents are better for complex, dynamic situations. Utility-based agents excel when there are multiple ways to achieve a goal, and learning agents are ideal for environments that change or require adaptation. Understanding these differences helps developers build more effective AI solutions. Each kind of agent program combines particular components in specific ways to generate actions. For example, simple reflex agents rely on condition action rules, while model-based agents use internal models and percept history. Goal-based and utility-based agents incorporate planning and evaluation, and learning agents add mechanisms for feedback and improvement. The combination of these components determines how the agent behaves and adapts. Agents are used in a wide range of real-world applications. Simple reflex agents can be found in basic automation systems like thermostats. Model-based agents are used in robotics and navigation. Goal-based and utility-based agents power intelligent assistants and self-driving cars. Learning agents are at the heart of advanced AI systems, such as recommendation engines and adaptive robots. The choice of agent type depends on the complexity and requirements of the task. Let's revisit simple reflex agents in action. In a factory setting, a simple reflex agent might control a conveyor belt, stopping it when an object is detected and starting it again when the path is clear. This straightforward approach works well in environments where the rules are clear and the agent doesn't need to remember past events. However, if the environment becomes more complex, this type of agent may struggle. Model-based agents are commonly used in robotics. For example, a robot vacuum cleaner uses sensors to map out a room and remember where it has already cleaned. By maintaining an internal model of its environment, the robot can avoid cleaning the same spot twice and can adapt if furniture is moved. This makes model-based agents much more efficient and capable in dynamic settings. Goal-based agents are essential for navigation tasks. Consider a GPS navigation system that helps you reach your destination. The system sets a goal, your destination, and plans the best route to get there. If there's a road closure or traffic jam, the agent can replan its route to ensure you still reach your goal efficiently. This proactive planning is a hallmark of goal-based agents. Utility-based agents are widely used in decision-making systems. For instance, in financial trading, an agent evaluates different investment options based on potential returns and risks. By assigning a utility value to each option, the agent can choose the investment that offers the highest expected benefit. This approach ensures that decisions are not just goal-oriented, but also optimized for the best possible outcome. Learning agents are at the core of adaptive systems. For example, a recommendation engine on a streaming platform learns from your viewing history to suggest new content. As you watch more shows, the agent updates its recommendations, becoming more accurate over time. This continuous learning process allows the system to adapt to your preferences and provide a personalized experience. Despite their simplicity, simple reflex agents face significant challenges. In partially observable environments, they can't access all the information needed to make the best decisions. This often leads to repetitive or ineffective actions. Additionally, they can't handle tasks that require memory or learning, making them unsuitable for complex or changing environments. Model-based agents offer several advantages over simple reflex agents. By maintaining an internal model of the environment, they can handle incomplete information and adapt to changes. This makes them suitable for tasks like navigation, robotics, and any situation where the environment isn't fully observable. Their ability to predict and plan sets them apart from simpler agents. Planning is a key feature of goal-based agents. They don't just react, they think ahead. By considering possible sequences of actions, these agents can choose the best path to achieve their goals. This makes them ideal for tasks that require foresight, such as route planning, scheduling, and problem-solving in dynamic environments. Utility-based agents excel at optimization. They evaluate different actions based on a utility function which quantifies how desirable each outcome is. This allows them to make decisions that maximize overall benefit rather than just achieving a goal. In fields like finance, logistics, and resource management, utility-based agents help organizations make smarter, more efficient choices. Continuous improvement is the hallmark of learning agents. Unlike other agents, they don't just follow fixed rules or plans. Instead, they learn from experience, adapting their behavior to become more effective over time. This makes them invaluable in environments that are unpredictable or constantly changing, such as online services, robotics, and adaptive control systems. Simple reflex agents are best used in situations where the environment is fully observable and the rules are straightforward. Examples include basic automation tasks like turning lights on or off based on motion sensors. In these cases, the simplicity of the agent is an advantage, as it ensures quick and reliable responses without the need for complex processing. Flexibility of model-based agents makes them suitable for a wide range of applications. They can adapt to new information, remember past events, and predict future outcomes. This flexibility is crucial in environments where conditions change frequently, such as smart homes, autonomous vehicles, and industrial automation. Goal-based agents are proactive, always working towards a specific objective. This makes them ideal for tasks that require planning and decision-making, such as project management, logistics, and strategic games. Their ability to evaluate different scenarios and choose the best course of action sets them apart from reactive agents. Utility-based agents focus on achieving the best possible outcomes. By evaluating the utility of different actions, they can make choices that maximize satisfaction or efficiency. This approach is especially useful in complex decision-making environments where there are multiple ways to achieve a goal and some options are better than others. Adaptation is the key strength of learning agents. They don't just follow instructions, they learn from their successes and failures. This allows them to handle new challenges, improve their performance, and even discover better ways to achieve their goals. In rapidly changing environments, learning agents provide the adaptability needed to stay effective. Designing an agent program involves selecting the right components and combining them effectively. For simple tasks, a set of condition action rules may be enough. For more complex tasks, you might need to add models, goals, utility functions, or learning mechanisms. The design process is about balancing simplicity, flexibility, and intelligence to create an agent that meets the needs of the environment. All agents can improve their performance over time, but learning agents take this to the next level. By analyzing feedback and exploring new actions, they continuously refine their strategies. This ongoing improvement is essential for long-term success in complex or changing environments, ensuring that the agent remains effective as conditions evolve. Adaptability is a crucial feature for modern agents. Whether it's adjusting to new information, changing goals, or unexpected obstacles, agents need to be flexible. Model-based, goal-based, utility-based, and learning agents all offer different ways to achieve adaptability, making them suitable for a wide range of applications in today's fast-paced world. Spectrum of agent intelligence ranges from simple reflex agents, which are fast but limited, to learning agents, which are slow to start but become highly effective over time. Understanding where your application falls on this spectrum helps you choose the right agent type and design the most effective solution. As AI technology advances, agents are becoming more intelligent, adaptable, and capable. The future will see even more sophisticated agents that can learn, plan, and optimize in real time. These advancements will open up new possibilities in fields like healthcare, transportation, education, and beyond, making intelligent agents an integral part of our daily lives. To recap, we've explored 5 main types of agents: simple reflex, model-based reflex, goal-based, utility-based, and learning agents. Each type offers unique strengths and is suited to different tasks. By understanding these differences, you can design AI systems that are more effective, adaptable, and intelligent. Key takeaway is that agents are the building blocks of intelligent systems. By choosing the right type of agent and combining the right components, you can create AI solutions that meet the needs of any environment. Whether you need speed, adaptability, planning, optimization, or learning, there's an agent type that fits the bill. Agents are all around us, powering everything from smart home devices to advanced robotics. As AI continues to evolve, agents will play an even bigger role in making our lives easier, safer, and more efficient. Understanding how they work is the first step to harnessing their full potential. Looking ahead, the possibilities for intelligent agents are endless. As we continue to develop smarter, more adaptable agents, we'll unlock new opportunities in every industry. The journey of AI agents is just beginning, and the future promises even greater advancements. Conclusion: understanding the different types of agents is essential for anyone interested in artificial intelligence. From simple reflex agents to advanced learning agents, each type plays a vital role in the development of intelligent systems. By leveraging their unique capabilities, we can build AI solutions that are smarter, more efficient, and better suited to the challenges of tomorrow.